Okay, guys, we're going to continue on discussing torque. On my last video, I think I got cut off, so I'm going to pick up where it left off. So this is going to be torque notes part 2. I'm only allowed to record 15 minutes of video at a time, and it cuts me off using this application. So where I left off was explaining how this portion, r sine theta of the torque formula, is known as a leverage, or also known as lever arm length. So going back to my example of pushing on a door, this could be a door, this could be a wrench, it could be anything. This is a rotational axis. This is a lever arm I'm pushing on, all right, or pulling. So right now, I am not maximizing my torque, all right? Let's, for ease of thinking, let's say the hardest to push is 200 newtons. It's not very hard, but let's just say the hardest I could push is 200 newtons. So if I push at a lower R that's possible, and especially in conjunction with a non-perpendicular angle, I'm not getting as much torque out as I can. Because remember, torque equals FR sine theta. That means it's going to be harder to open that door. So what I want to do to maximize my torque, especially if I can't push any harder, again, I'm pretending I can only push at 200 newtons. That's as strong as I am. What I want to do, if possible, is to go as far away, push as far away from the axis of rotation, and this is still going to be 200 newtons, and that's going to maximize my R. But remember, we could do two things to maximize my leverage if possible. One of those two things is to increase my R as much as possible, and the second thing is to push perpendicular. So the sine of theta is 1. So torque equals FR sine theta. So in this circumstance, if I really am pushing as hard as I can, I will get the max torque out in this situation because I have the biggest R possible. I can't go any further out on this lever arm, and I'm at 90 degrees for the theta. And that's why we, without thinking, push on doors or pull and push on wrenches as far away as possible. Yeah, you might not have known what torque was, but somewhere in your life you felt it and you have the idea of it inside you. Just knowing it makes things easier to maximize your leverage. All right, with that in mind, we're going to go to the example problem at the end of these notes, which just uses this single formula in different ways. Hopefully it should be pretty easy to follow, then you guys will have practice problems on this idea. All right, so let's take a look at this situation. A force of 200 newtons is placed perpendicular on a wrench 0.45 meters away from the bolt it's trying to loosen. All right, I'm going to draw a really rough, bad diagram here. So here's my wrench. All right, and this red thing is going to be my bolt I'm trying to loosen right here. And my force is going to be placed 0.45 meters away from the bolt. So let's say it's like right there. And that force is the 200 Newton force. So we'll say that force equals 200. Okay, so this would be, remember, R is the distance where the force is applied to the axis of rotation. The axis of rotation is where the wrench head is on the bolt. So that would be 0.45 meters. And it does tell me the angle is perpendicular. That's why I drew that force in that fashion. So for part A, using that information, it says find the torque the wrench places on the bolt. So torque equals FR sine theta, and that's 200 multiplied by 0.45 times the sine of 90. But remember from before, the sine of 90 is 1. So here again is if I'm at the end of the wrench. If the wrench is about 0.45 meters long and I'm pushing it or pulling 90 degrees, I'm maximizing my leverage right now. The only way I'd be able to get more torque is if I pushed or pulled harder than 200 newtons. So I'm going to quickly calculate these values. So 200 multiplied by 0.45 times the sine of 90 is actually equal to 90. And remember the units, Newton meters. Let's take a look at some variation of this. Let's go to part B. In part B, we're going to change something. We're still going to use the same force, 200 newtons, but now we're going to change one thing, the angle. No longer am I going to push or pull at 90 degrees. I'm going to change it, and my force is going to be like more like this, my new force, and it's going to be at 35 degrees. So I'm going to lose some leverage here, which should show, if we have the concept right, that I'm not going to be able to get as much torque, even though I have the same R, 0.45, even though I have the same force, 200. If I don't push perpendicularly, and I do FR sine theta again, I'm going to get 200 times 0.45. That part doesn't change. It's sine of 35. Now, you are going to need a scientific calculator to do these problems. However, if you don't have one at home, you could get one. You might already have one on your phone. There should be one loaded on these Chromebooks as well. So if you have your Chromebook, that shouldn't be a problem. You could get, there's tons of free apps out there with scientific or graphing calculators. We should all be able to get if we don't already have one. So 200, actually, let me start over there. All right, so 200 times 0.45 times the sine of 35. I'll have that answer for us in 1 second here. And it comes out as about 51.6 Newton meters. And you notice something that is lower compared to part A. So like I said, even though we're pushing or pulling with the same force, with the same R, 0.45, because I'm not at 90 degrees, I lost some leverage. And it becomes harder to rotate that object because I can't apply as much torque. Maybe that thing doesn't even rotate, possibly, because I can't apply enough torque. Regardless, the number is lower. And finally, part C, it says find the lever arm length, aka leverage, when the force is placed at 35 degrees. So remember, the lever arm length, or leverage, L, is just part of the torque formula. It's just the part excluding F. So it's just R sine theta. Make this harder than what it is. It's a simple idea. So that would just be 0.45 times the sine of 35. So let's run the numbers here. I multiply those two values. The leverage I'm getting at 35 degrees is equal to 0.2, I'll round it, about 0.26 meters. This is the length, though it is in meters. Now I want to point something out here. We grasp the concept, all right? In part A, since we're at 90 degrees, didn't ask us to do this, but the leverage in part A would have been 0.45 times the sine of 90. But as you recall, the sine of 90 is 1. So if I am pushing or pulling perpendicular, the R value is the same as leverage, because sine of 90 is 1. But when I go off perpendicular, if I keep the R the same, like I did here and here, but I don't go perpendicular and this angle changes, then I lose leverage. what this is kind of telling us is that if I could push or pull perpendicularly with this wrench, I would have a 0.45 meter lever arm. But since I'm not pushing and pulling perpendicular, in this case at 35 degrees, it's as if I'm pushing or pulling to apply this torque on a smaller